Hi, in this presentation we'll cover Gouraud interpolation and Phong interpolation. So far we've talked about Phong lighting, not to be confused with Phong interpolation. Phong lighting took a point X on a surface and one light or multiple lights and computed the illumination of the point as seen by the viewer at that point. That's all very well and good, but of course we're interested in rendering triangles in order to render surfaces that look smooth. To render surfaces that look smooth, we want the colors to vary smoothly across the surface in a way that hides the triangular nature of the geometric model of the surface. So the situation is, we've got some triangle that we're rendering on the screen. And it's got three vertices, which are at some positions in space, x1, x2, x3. And they end up on some pixels on the screen. The Phong lighting uses the positions x1, x2, x3. It also uses the normals at those positions, n1, n2, n3. And it uses, of course, material properties and light properties and the position of the viewer and so forth to compute colors at these three vertices, which I'll call C1, C2, and C3. So think of C1 as a vector of red, green, blue values. C2 and C3 similarly are vectors of red, green, blue values. And we'd like to render, however, the whole triangle on the screen as pixels. So have some pixel on the screen in the middle of the triangle. This should get some color C. And the question is, what color does that get? So there's several methods for this. So what color should be assigned to pixels inside the triangle? And there's two standard methods for this. The first one I'm going to discuss is Gouraud interpolation, also called Gouraud shading. The two terms are used interchangeably, Gouraud interpolation and Gouraud shading. And the second one is Phong interpolation, also known as Phong shading. So let me mention right now that so far in the previous presentations we've talked about Phong lighting. Now we're talking about Phong interpolation or Phong shading. Those are different things. Phong lighting is something different than Phong interpolation, Phong shading. Phong lighting can be used either with Gouraud interpolation or with Phong interpolation. So the easier one is Gouraud interpolation. So let's do that first. So Gouraud interpolation, the general idea is you compute color values C1, C2, C3 at the three vertices. And then average or interpolate or shade those to get color values C for pixels in the middle, pixels inside the triangle. So that's the general idea of Gouraud interpolation. Phong interpolation and it's named Phong interpolation because that's what Phong actually proposed in his original paper on Phong interpolation. Gouraud suggested this alternate method of Gouraud interpolation later on. So here what you do is you compute X and N values for pixels inside the triangle. And then do Phong lighting for each pixel. So in the picture here, we would compute a position x and a normal n as an estimate for where the surface is for that intermediate pixel. And then we would redo the Phong lighting calculation for each pixel in the triangle. So I'll go into these in a little more detail on the next boards. So for Gouraud interpolation, we start with the calculation of C1, C2, C3 for the three vertices. So then an intermediate pixel like this one shown here gets color C equal to a weighted average C is alpha C1 plus beta C2 plus gamma C3 with, as a weighted average, we have alpha plus beta plus gamma equals 1. And alpha, beta, gamma are all greater than or equal to 0. And so we just take the coefficients alpha, beta, gamma depend on where in the triangle the pixel is. If the pixel is close to C1, alpha will be really big. If it's close to C2, beta will be really big. If it's close to C3, gamma will be really big, and then it varies smoothly in between those two things. This is basically what's using, this is using what are known as barycentric coordinates, a topic we'll take up in future presentations. For now, it's enough to just think of it's a blend, that C is a blend of the colors C1, C2, and C3. We're going to use barycentric coordinates and hyperbolic interpolation. These are topics for future presentations. And in this way, we just, having done the Phong calculations, the Phong lighting calculations at the three vertices, we average those values to get the intermediate color. So basically smoothly varying this across. So the advantages of this method, there's actually a number of them, but there's also some very serious disadvantages. So the advantages include it's quick to compute, easy to compute, C from C1 and C2 and C3. And in fact, it's even built in to OpenGL to do this kind of averaging. This kind of averaging with barycentric coordinates and hyperbolic interpolation is so useful that it's a built-in feature in OpenGL, so it can just happen more or less automatically for you under the behind the scenes without having to code this up in any way. This is what typically happens when we have variables sent out from the vertex shader and sent into the fragment shader, is they get averaged in this way that I'm describing here. So the disadvantages, however, are also rather serious. So a big one is that the normals may shift, and the positions, of course, shift as you go across a triangle. So what can happen is, if you had a spotlight shining, say, in the middle of a triangle that didn't hit the vertices, you would just miss completely seeing the spotlight on the surface. So you can miss things like spotlights. You can miss miss spotlights, can miss specular highlights. So if you have a small specular highlight, it might be located primarily in the center of a triangle, and you just wouldn't see it because when you do the Phong lighting calculations for the 3 vertices, they would not be inside the main part of the specular highlight, so we wouldn't get the specular highlight at the vertices. When you average across, you still wouldn't get the specular highlight there. So you can miss specular highlights, you can miss spotlights, and it can also, in general, can look very bad with animation, because what happens with animation is even if you don't completely miss specular highlights, the normals will, as you animate, may move the vertices in and out of the center of specular highlights, so you get this sort of easily visible fluctuation in the surface illumination that can look really bad when you're moving around. And so in particular, to get over these disadvantages, you may need to make your triangles very small for it to look good. You may need to make triangles be very small to look good. Okay, so we'll do Phong interpolation next. For Phong interpolation, we, instead of averaging the colors, we average the position and the normals, and then redo the Phong lighting for every pixel with a new position and normal. Again, let me stress that Phong interpolation is different from Phong lighting. Phong lighting is this calculation of I in terms of I sub A, I sub D, I sub S, and I sub E, where we used the L, N, and V vectors and so forth, material properties and light properties. It was a big complex computation for the light at a particular point. Phong interpolation, as compared to Phong lighting, means to how we do colors at intermediate points in triangles. So for Phong interpolation, we compute a position X and a normal N for a pixel inside the triangle by averaging. Okay, so instead of averaging the colors, we're averaging the normals and the positions. So X will end up being something like alpha X1 plus beta X2 plus gamma X3. It's a weighted average of the positions of the 3 vertices in space, and this then is computed with the same kind of coefficients, alpha, beta, gamma, as I discussed on the previous board for the color. And the normal, it would likewise be alpha N1 plus beta N2 plus gamma N3. In general, that's not a unit vector, but we make it back into a unit vector by dividing by its magnitude. So we have the weighted average of the 3 vectors divided by their magnitude to generate a new unit vector n. These values then are used with Phong lighting, not Phong interpolation, Phong lighting, to compute an illumination level, to compute the color value C. So this can give much higher quality results than Gouraud interpolation. So the advantages here, better quality results. You don't miss specular highlights. You don't miss spotlights. It's good behavior with specular highlights. I would say excellent behavior with spotlights usually. It's excellent with spotlights. Because spotlights depend just on position, not on normals typically. It's good behavior on animation. So you can get away with bigger triangles. You can use bigger triangles than were used for Gouraud interpolation and still get the same type of quality result. The main disadvantage is the computation is slower. Computation time, because you have to do the Phong lighting calculation at each pixel. The Phong lighting calculation is a relatively expensive computation, and that's a lot of work to do at each pixel. So you have to do Phong lighting at each pixel. Nonetheless, even with this extra computation time, graphics processing units, GPUs, are so powerful nowadays that I would say Phong interpolation is a much more popular choice when available than Gouraud interpolation, just because the quality is so much better. And that's the end of this presentation. Thank you very much.